Okay, in this video, I want to talk about antennas, because we seem to be living in a wireless world. We use our cell phones, Wi-Fi, Bluetooth, and Internet of Things is growing in popularity with the LoRa system. So without the use of a proper antenna system, you won't be able to communicate at all. So the antenna is an important component in the wireless world. Now if you've been involved in a radio project, you've probably seen an antenna like this. This is called a helical antenna, and they're very popular because they're very short. They're shorter than the quarter wave monopole. They're vertically polarized, and they're wound in a helix. It's like a spring. So when the diameter of this antenna is a lot smaller than the operating wavelength, it will operate in its normal mode. Now in the normal mode, the radiation pattern of this antenna will be the same as a quarter wave monopole. Okay, the radiation pattern of a quarter wave monopole is the same as this helical antenna operating in normal mode, and we call the radiation pattern omnidirectional, equal in all directions. And it's in the shape of a donut. I don't have a donut, but I have a bagel. It's basically the same thing. So that would be the radiation pattern of this antenna, except in real life it would be a very large bagel. Now if you look at the top view, the horizontal view, you can see it's omnidirectional. And if we look at the vertical view, the side view, we can see all the power is coming off the sides of the antenna, perpendicular to the antenna. And we have a null on the top, and we have a null on the bottom. Now if we look at another antenna, this one here, this one has the same operating frequency as this antenna, except this is a gain antenna. This is a 5/8 whip, base loaded, and it's a gain antenna, so they're usually larger than its counterpart because it has a bigger aperture. Now when we talk about gain antennas, it does not create power because it's a passive device. What it does is focuses the same power density in a certain direction. So if you look at the vertical pattern, in the gain antenna, it squeezes the lobe like this to get more power in this direction. So it takes power from the top of the lobe and the bottom of the lobe, and it squeezes it to give more power in this direction. So we're not creating power, we're just focusing the power. Okay, if you look at the back of your stereo, where your speakers are connected, you'll see a label there saying 8 ohms output or 4 ohms output. Now if it says 8 ohms output, you have to hook up an 8 ohm speaker or an array of speakers that equals 8 ohms to the output of your stereo. And if it says 4 ohms output, you have to hook up a 4 ohm speaker to your stereo. Now we do this to get maximum power transfer from your stereo to your speakers. And this holds true also for an audio amplifier. Now if you have an audio amplifier with output impedance of 1k ohm, and you hook up an 8 ohm speaker directly to the output of that amplifier, you'll get a mismatch and you won't get maximum power transfer. It'll actually be shorting out your amplifier. So what you could do is add a matching transformer, and they look something like this, with a primary impedance of 1k ohm and a secondary impedance of 8 ohms. So now you can match the output of the amplifier to the speaker, and you'll get maximum power transfer. Now that holds true for a radio system. So if you had a radio that has a 50 ohm output, and it's feeding an antenna with a 50 ohm input, so we're getting maximum power transfer between the radio and the antenna. But now the antenna has to match the free space impedance of 377 ohms. So basically the antenna is a matching device. It's like a matching transformer that matches the 50 ohms to free space of 377 ohms. And if you could do this, you'll get maximum power transfer from the radio to free space. So you'll get maximum electromagnetic radiation from the antenna. So we'll look at a couple of antennas, two common antennas that can actually do this. So here's our setup. We have a radio with a 50 ohm output, and it's feeding a transmission line that has a characteristic impedance of 50 ohms, and that's feeding our antenna. Now the two antennas we're going to look at are the dipole, the half-wave dipole, and that has an input impedance of 73 ohms, and a quarter wave monopole that has an impedance of 37 ohms. So we're going to get a little bit of a mismatch, and the amount of mismatch is indicated by the VSWR value. That's the amount of RF power that's reflected back from the antenna back to the transmitter. Now since the VSWR is less than 2 to 1, we could accept that. So next we're going to look at the monopole antenna, and we'll actually see how we could actually build one of these. Okay, I have a piece of coaxial cable. This is RG58. It's got a characteristic impedance of 50 ohms, and I have an RF cable on one end, and on the other end it's open circuit. So if I turn on the transmitter, all the RF power will come up to open end, and all of it will be reflected back towards the transmitter. So I will have a very high VSWR, and there'll be no radiation coming out of the cable. But if I strip back the cable and bring out the center conductor and the braid like this, now I got myself a dipole antenna. Now I have maximum radiation. Now the input impedance of this antenna is 73 ohms, so I have a little bit of a mismatch. So 73 divided by 50 is around 1.4, and that will be the VSWR, and it's less than 2, so we could accept that. Now because the current in the braid is in the same direction as the current in the center conductor, it enables this antenna to radiate. Okay, I reconfigured my dipole antenna into a quarter wave monopole with a ground plane. And you can see here my quarter wave radiator. And I have 4 radials which act as my ground plane. Now the ground plane is actually like a mirror. So the antenna sees another quarter wave radiator in the reflection of the mirror, so it acts like a dipole. Now the input impedance of this antenna is 37 ohms, but if you droop down the radials at a 45-degree angle, you can get the input impedance up to 50 ohms. So next we're going to look at how to build one of these that you can use in your project. Okay, if you're going to build one of these quarter wave monopole ground plane antennas to replace one of these helical rubber ducky antennas, expect about a 6 dB increase in signal, which could double your range, because these helical rubber ducky antennas are pretty inefficient. So what you could do before you start building your antenna is build one out of coaxial cable like I showed you in the last clip. And if you like the performance, then you could start building your permanent antenna. So to start off, get yourself a chassis mount, female end connector, like this one here. And it has 4 holes for mounting it onto a chassis, and we're going to use those to solder in our radials. So then get some electrical wire, like this, and strip out the copper, and cut 5 pieces of copper the same length, and solder in 4 for your radials, and 1 for your radiator. Okay, here's the formula to calculate the length of the 4 radials and the radiator. Now the velocity of propagation factor is built into this formula. So I built my antenna for 2.4 gigahertz. So you see here the formula, it worked out to 1.18 inches for my radials and my radiator. Now I bent down my radials at a 45-degree angle so I could get a better match at 50 ohms. Now when you design an antenna for a lower frequency, the lengths will get longer. So if they get really long, you might have to go into some stiffer wire, like maybe welding rods, which you could pick up at a hardware store. Okay, to complete your project, you could hook up the transmission line up to the connector on your antenna. Now if you're doing a short run, you could use RG58 cable, but if you're doing longer runs, you should use some low loss cable like RG213 or LMR400. Now if this antenna is going outside, you should put some hot glue on the base of the radiator to keep the water out. Now to mount this antenna, you get a little short pipe and bring it up over the cable and over the connector, and then cut slits in the pipe, and you can clamp it down with a stainless steel hose clamp. Then you get some vulcanizing tape and some black tape and seal up the whole antenna. Now to mount this antenna, it will be very easy now, because you have a pipe which you can mount to the side of a building.